Hi, this is Jeremy, one of the authors of the textbook Machine Learning Refined. I'm showing you our GitHub repo here. In this video, I'm going to walk through the Jupyter notebook called Nonlinear ML, Kernels, Neural Networks, and Trees. That's what the rest of this says here. I'm going to be working from the Docker image of this GitHub repo, which you can pull by running the following command at your terminal after installing Docker. But you can also pull this GitHub repo like you would any other, or click here to launch a live instance of the repo to follow along with me. Here I have my Docker image all set up, and I've already started the notebook. This notebook contains a number of interactive demonstrations that supplement Chapter 5 of the text on general nonlinear regression and feature learning. In particular, this provides live demos of the three main algorithms for nonlinear regression that is kernels, neural networks, and trees. Now, this is a very long notebook with lots of text-based description in it. So when I walk through, I'm just going to give you the high-level overview of what each of the demos do. But if you want to learn more about it, more precisely about what's going on, please do look at the notebook and read the text, as well as play around with the interactive demos. Let's get started. The first printout here shows a generic nonlinear regression data set. Those are the black noisy points. Now, underlying any nonlinear regression data set like this is a true underlying function, here shown in dashed red. This is the rule that creates our data set. We don't know what that rule is. We have to try to infer it from the noisy data we receive. But the basic point of nonlinear regression is to try to, using the data we actually have, approximate this underlying rule or this underlying data generating function. So in particular, what we need is a formula for our approximation to this underlying function. And why do we want that? Because we want to be able to use that formula in the future. If we get new inputs, we can predict new outputs based on that formula. How do you get at that formula? What you do is you take a collection of functions whose formula you already know. Those are usually referred to as a basis. Those come in a variety of forms, but there are three basic types of mathematical bases. Those are kernels, neural networks, and trees. We take one of those collections. We then add them up in a special way using numerical optimization. That gets us an approximation to an underlying function like this. Because we know the formula for each element of those bases, when we add them up in a special way, we still know the formula of the sum, and therefore we have a formula for an approximation to this basis, to this underlying function. That's what the middle part of this notebook describes. So if we scroll down to the first section of the notebook, we talk first about an instance of a kernel type basis, polynomials. Those might be familiar to you. They look like this. The first element is f of x equals x, x squared, x cubed, and so on. The first Python cell here, when you activate it, plots the first couple of elements of a polynomial basis. So that is f of x equals x, x squared, x cubed, x fourth, etc. A polynomial is an instance of a fixed kernel basis, right? The formulas are fixed, of course. You have x, x squared, x cubed, etc. But the shape of the bases are also fixed, right? F of x equals x always looks like this. F of x equals x squared always looks like a parabola, right? There's no parameters in either of those basis elements or any of the polynomials that allow you to adjust their shapes. We're going to see that's not the case for neural networks and trees. In the next Python cell, you activate this cell, and what you see here is a demonstration of how polynomials can be fit to a true underlying data generating function. That is, say we have the data generating function itself that was shown in dash red above, but here I'm showing it in constant red. So that is, we don't have a noisy data set, we have an absolutely true perfect data set. The slider here, as you run from left to right, shows you what it looks like when you fit starting from one polynomial basis element to two polynomial basis elements when you slide from left to right, to 3, to 4, to 5, 6. So as you slide from left to right, you see the resulting fit of so many elements from the polynomial basis. And after you get to about 3 or 4, the fit is pretty much perfect. As you go from left to right, of course, the fit gets better and better. You're using more polynomials, you have the true underlying function, and the fit just gets better and better. In the next Python cell, you can see a demonstration of fitting a polynomial basis to a noisy data set. Actually, it's the same one we saw above. Now that true underlying function is shown in dash red. Right? As we move from left to right, we're going to be fitting more and more polynomials, not to that underlying function, but to the actual noisy data set. Now note, as you move from left to right, say we're at 3 elements, the fit is pretty good there. That is, the blue approximation gets at or approximates the red dashed underlying function pretty well. Unlike the case above, right, where if we keep moving the slider to the right, that is, we continue to use more and more basis elements, the approximation gets better and better as we move from left to right. That's only the case up to a certain point here with the actual realistic data set. If we go too far, our approximation doesn't get better, it actually gets worse. Well, in particular, it gets better in terms of modeling the actual data that we have. But it gets worse in terms of modeling or approximating the underlying function itself. This phenomenon is known as overfitting. And this is why you need to use what's called cross-validation to pick the number of basis elements you use in practice. Because if you use too many with a real data set, you get what's called overfitting, and you're no longer approximating that underlying function the way you want to. All right, in the next section, we talk about neural network bases. So this is a different kind of basis element you can use to perform nonlinear regression. Each of the basis elements, in its simplest form, looks like a function, each of them a simple elementary function that has parameters inside of it. So for example, you can have a basis of neural network elements that look like this. F of x equals max of 0 and a linear combination of the input. Now each one of these, because there are parameters inside, they're flexible. They can take on a variety of shapes. You can see some examples of those shapes by activating this next Python cell. Every time you activate this cell, you get 4 random instances of that basis, that single basis element. So if I activate it again, I get 4 new instances of that individual basis element. Okay? Unlike polynomials, this single basis element can take on a variety of shapes, okay, as shown here. Now we can get more complicated with our neural network basis elements. You can compose those parameterized functions with each other. This is an example of another kind of neural network basis element that has what's called several hidden layers. You can see it's a composition of a max of 0 and a linear combination of max functions. So there are a lot of parameters inside of this single basis element. You can see some of the shapes this element can take by activating the next Python cell. When you activate this, you get 4 random instances of this basis element. So if I activate it again, I can see 4 more shapes. All of these shapes are taken by this single basis element. In the next Python cell, you can see what are even more complicated neural network basis elements. You can see instances of even more complicated elements. So if I activate this cell, you can see I get even more complicated looking shapes than what I can get out of just this basis element here. Essentially what you can do is continue to compose elementary functions with themselves. So I can take max of max of max, get even more parameterized basis elements, and those basis elements take on even a wider variety of shapes, like what's shown here. In particular, there are 20 hidden layers for this demonstration. You can play around with this parameter, increase the number of layers, that is the number of compositions of the elementary function, and just see how crazy the variety of shapes you can get out of a single basis element become. Now, like the polynomial example above, the next demonstration shows you what it looks like to fit a set of neural network basis elements to a true underlying function. In the original example, this was shown in dashed red, but it's shown once again in constant red here. Again, when you activate this cell, what will pop up is a slider. As you move this slider from left to right, you're fitting more and more basis elements to the underlying data generating function. As with the pure example with polynomials, the further you move this to the right, the better you're going to fit the underlying function. The next Python cell shows you that that realistic noisy nonlinear data set with the true underlying function shown in red. Remember what we did here with polynomials. As we moved the slider from left to right, we added more polynomials into our approximation. But there was a sweet spot. When we moved from left to right a little bit, we got a better approximation of the underlying function. But if we move too far, we get something that doesn't fit the underlying function as well. This is the same. This phenomenon is absolutely mirrored with neural network basis elements. So there's a sweet spot with a realistic data set. Unlike a true underlying data generating function, it's not the case that the more basis elements you use, the better the approximation becomes. After a certain point, the approximation gets worse. It fits the data better, but it doesn't fit the underlying data generating function better. So that's why you need what's called cross-validation. That helps you pick the right set of parameters or the right number of basis elements to get the best approximation to that data generating function that's possible. Finally, we can look at trees. Tree basis elements are another class of bases that are commonly used for nonlinear regression. They aren't continuous, right, like polynomials and neural networks were, right? They're actually semi-continuous or piecewise continuous. They look like this in one dimension. You have a step on one side of a separating point that's fixed at a constant height. Then on the other side, you have another step that's fixed at a different constant height. That's the simplest kind of tree basis element. It's called a stump. If you activate the first Python cell in this section, you can see 4 instances of a single stump, right? Because the parameters being adjusted here are the splitting point and each of the heights. So one basis element can take on a variety of shapes. In that sense, it's similar to a neural network basis element, where each individual element can take on a bunch of different shapes. Unlike a polynomial kernel fixed basis element, where each basis can take on only one fixed shape. Of course, you can get more complicated with the trees, right? Instead of splitting once, you can split a number of times. On each section, on each split, you have a different height that you can choose. So each of these becomes a parameter. The location of the splitting points, the heights of each segment. This gives you a basis element with an even wider selection of shapes. So if you activate this cell, you can see 4 random instances of a basis element of this form, where you have several splits. Of course, you can get more complicated too. You can add more splits that gives you more levels. And in this Python cell, you can adjust the depth or the number of splits on the tree basis element and create 4 random instances, and you can just see this is one basis element, and these are all the different kinds of shapes you get when you add more and more splits. As with the polynomial and neural network basis elements, the next demonstration allows you to fit a tree to that true underlying data generating function. As with polynomials and neural nets, the more we use, the further I slide this to the right, the better the approximation becomes. Okay? The more basis elements we use, the better the approximation. However, as we've seen previously with the other 2 bases, we activate the next cell. This allows us to fit trees to that realistic data set. And as we move from left to right, as with polynomials and neural networks, there's a sweet spot. Okay? When we use a certain number of those basis elements, we get a good fit to the data generating function. But if we use too many, we start to fit to the data set better, but we start to fit to the data generating function worse. And so once again, cross-validation needs to be used here to pick the correct number of trees to use. The next section of the notebook contains several demonstrations that try to give you some intuition about when you should use which type of basis in practice. So if we scroll down to the next section, it's out of which bases should I use? In short, which basis you should use well, it depends on the shape of your underlying data generating function. In the example we've looked at throughout the notebook, okay, we have a sinusoidal underlying generating function. That's something that's continuous. It has fairly mild curvature. And so something like a polynomial or a neural network is going to do a very good job at approximating the underlying function well. You can see that by playing again with the demonstration that we saw in the polynomial section. So as we go from left to right here, right, we need to pick the number of basis elements we use correctly. That's what we do when we slide the slider from left to right. We're changing the number of polynomials that we're using. And remember, there's a sweet spot, okay, that in practice has to be chosen using cross-validation, but here we can just use the slider. And you can see when you choose that number correctly, here it's 3, you get a pretty good fit to the underlying data generating function. That's because the polynomial basis itself is well suited for this to approximate this kind of underlying function, right? The underlying function, it has mild curvature, it's continuous, and those characteristics you could say, well, that's what a polynomial basis has as well. We can do the same experiment again with a neural network. For a particular choice of function, if we choose the number correctly, say 4, we get a very good fit to the underlying data generating function. Why? Because this neural network itself, the elements of this neural network are continuous and their curvature is rather mild as well. So when we choose the right number, here using the slider, but in practice by cross-validation, we'll get a very good approximation to the underlying function. Now this is not the case with the trees, right? Now why is that? Okay, even if we pick the number correctly, the number of elements to use, say around 3, maybe 4. Well, we've chosen the number correctly, and this is what we would choose essentially using cross-validation. But we don't get as good a fit to the underlying function, and why is that? Well, because trees are not continuous, right? Trees, and they also do not have mild curvature. They're very zigzaggy, okay? So there's no way we can use this to get a good approximation to the underlying function unless we have a bunch of data, right? Unless we essentially have every single point on the true underlying function. Then we can increase the number of basis elements that we use and we get a good approximation. But in practice, with a generic data set like this, we're never going to be able to approximate that underlying function very well because the shape of our basis doesn't match the shape of the underlying function. Now if we take a different example, like the one shown here, okay, this is a noisy data set that's generated using a tree. You find data like this very often when you're exploring metadata like census information or a lot of data that's generated by e-commerce. So if we pull this into the Jupyter notebook, we can then do our experiments again using first a polynomial basis. And you can see in this instance, even if we choose the number of polynomials correctly using the slider, say around here, we still don't get a really good fit to that underlying data generating function because that underlying function looks like a tree, or it's not continuous and it has a bunch of zigzags in it. So our polynomial basis that doesn't look like that, right? The elements of a polynomial basis are continuous, they're smooth, they have fairly mild curvature. They're never going to be able to match something that is discontinuous and has a bunch of zigzags like this underlying function. This is the same deal with our neural networks. With only this amount of data, we can pick the number correctly. Right? In this case, we get a little bit of better fit to that underlying function than, say, with using the polynomials. But still, it's never really going to be able to match what's going on underneath the data very well because the underlying function doesn't look like the basis. It doesn't look like a neural network or a combination of neural network basis elements. It looks like a combination of trees. So in the last experiment, we can rerun fitting trees to that data set. And if we pick the number correctly, which we do in practice by cross-validation, look, we get a very good fit to that underlying data generating function. That's because the shape of the basis matches the shape of the underlying data generating function. How do you know what your data generating function looks like in practice? In general, you don't, and that's why you typically use all 3 types of these bases when you're solving a general nonlinear regression problem. You either use them independently and pick the best one, or you use them in some combination. There are specific instances where you can use your intuition about what the data looks like to try to infer what the underlying data generating function should look like. For example, with metadata, you often have discrete classes or discrete features. And the shape of that data generally matches the generic shape of a tree. So you can guess that a tree will typically work better for generic metadata than, say, a polynomial basis. Another example is with images. image data tends to be quite continuous. So you would suspect that a kernel or neural network typically works better for that sort of data. There are other instances as well, but in general, you'll try all three bases and pick the best result. There are a couple of other considerations you can keep in mind when choosing a basis as well. Some of them are computational in nature, and some of them have to do with whether or not you can scale your data in particular ways. Those are discussed in brief at the end of this notebook, and I'll leave those for you to check out if you want. Thank you. That's the end of the walkthrough for the Nonlinear Regression notebook. You can find a whole bunch of other notebooks that have similar fun interactive demos on our GitHub repo. You can find details on how to get to that repository in the description of this video. And if you want to learn more technical details about the content of this Jupyter notebook, check out Chapter 5 of our textbook, whose homepage is shown here at mlrefined.com.